Good morning. We are headed into chapter 4 today, and I just want to say that I know I said this about chapters 2 and 3. I said chapters 2 and 3 is where we really get into the physics. I'm going to say, starting with chapters 4 and 5, we're going to really get into the physics. And so what we do in these chapters is we introduce the idea of force. Up until now we've been doing kinematics, we've just been talking about motion, what are displacements, what are velocities, what are accelerations, how do we work in 2 or 3 dimensions. And I feel like we've done a good job. I hope, make sure that you're staying caught up. Keep coming to office hours with those questions. So we've provided some good examples for those. Now we want to say, how does all this happen? And it happens as a result of forces. And so what we're going to find is that when forces act on objects, when we have a force of some sort acting on an object, that creates an acceleration. If I have a bunch of forces acting on something, there's a couple of possibilities here. One possibility is all the forces cancel out. So in some situations, the forces all cancel out and there's no acceleration. But in other cases, the forces don't cancel out. There's what's left over, there's a leftover net force. And anytime there's a net force, that's going to lead to an acceleration. So here is the space shuttle just after launch. And it's saying that we have 2 different forces. We have a force of the propulsion system. So we have the thrust from the large boosters as well as the rocket motors on the shuttle itself, creating a forward force. And we have a gravitational force pulling back. So we're going to introduce gravitational force as well. So in order for the rocket system here to accelerate, the force of the thrust needs to be bigger than the force of gravity. Okay. Okay. They've got those labeled a little funny. That's why I'm staring at them. These are really, I'm going to say these are 2 different forces. They've got them labeled, anyway. Let's move on. I think we've said everything. Oh, the other item I wanted to mention is that the force is not the only determining factor determining what the acceleration will be. And so it's the force along with the mass. So if there's a lot of mass in an object, that creates an inertia effect. Heavier objects, objects with more mass, are harder to accelerate. And so it leads to this effect. More force leads to more acceleration, but more mass opposes the acceleration effect. Here's a list of all the topics we're going to be looking at. A couple of these I've highlighted. I've highlighted force and mass. I put a red highlight around weight, and that's because the word weight's a little dangerous. Weight gets used to represent the force of gravity. I don't think we should do that. We'll talk more about that when we get to the force of gravity. But this is a good diagram to start with here. So here is a shopping cart, and what we want to do is be able to isolate, in the examples we look at here, in this chapter and beyond, we want to be able to look at an object and identify which object we're looking at. In this case, it's the shopping cart with all the watermelons inside. Now, the shopping cart and the watermelons is the object. What forces are acting on it? So, the forces I'm thinking of is there's a force of gravity. So that's one of the forces here. There's what we call a contact force between the wheels, the little treads on there, and the pavement. So again, I'm isolating the shopping cart and saying from outside what's happening to it is there's a force from the pavement pushing up on the shopping cart, and I'm representing that with this vector here, this force vector, and calling it a contact force. Now, there is a force, I'm going to say that there's a force coming back, this is also a contact force, but this force specifically is what we refer to as friction, is what I'm guessing. I'm guessing that, most of the shopping carts that I've worked with have a fair amount of resistance in the bearings, and so when you push them, you can feel that there's an opposing force, and that's coming from static friction along the wheels. Now we'll look at friction in more detail in next chapter, but anyway, there's a contact force due to that, and then there's also a contact force due to the person pushing on the cart. So this cart has, I'm going to say, 4 different forces acting on it. Now, my guess is, this person pushing the shopping cart, it's probably constant velocity. And if it's constant velocity, that would say that the acceleration is 0. It's not accelerating, is my guess. If it's not accelerating, what that would say is that the contact force that the person is pushing with matches the contact force from the friction opposing that. So the person is pushing this, and there's an equal amount of force in the other direction, and as a result, there's no acceleration. Now, if the person needs to create an acceleration, if they want to go faster, if they decide to pick up speed, then the person is going to need to push harder. The person pushes harder, this force becomes larger, it becomes larger than the opposing force. Now I have what's called a net force. When I look at the forces, they don't balance out. So I've got more force forward than backward. There's a net force in the forward direction, and that will determine what the acceleration is, along with the mass. Now I got a lot of mass there. I've got the whole mass of the shopping cart and the mass of all those watermelons. So in this direction, I can sort of easily imagine an acceleration taking place. What would happen if the frictional force were larger than this forward push? If this friction becomes larger, then everything slows down, and that's also an acceleration. So if the force is balanced, there's no acceleration. If some of the forces are bigger than others, there will be an acceleration. Now, we've been speaking entirely in terms of horizontal motion, but what's happening in the vertical direction? Well, in the vertical direction, I'm guessing there's not going to be an acceleration. I'm guessing that the cart is not going to take off from the pavement and start heading upwards. And I'm also guessing that the cart's not going to collapse into the pavement. And that's happening because, well, there's a gravitational force downwards, but there's a support from the pavement. And as long as the pavement is sturdy enough to create a force that can offset the gravitational effect, then we'll have a net force of 0 in the vertical direction. So just like last chapter, we're taking these vectors, the vectors now are forces, and we're looking at the x components and the y components and making a comparison. All right, now here is a measuring device. What we've got is this spring-loaded thing, and it tells us how much force. We've got these numbers written here. Now, forces in standard units are measured in what we call newtons, and we'll take a look at the units here in just a minute. But here is this box with olive oil inside, and we've got what looks like kind of the same set of forces. I've got a gravitational force here. I've got a force upwards. Now this is a contact force, but this is specifically a contact force perpendicular to the surface. And we refer to those as normal forces. So normal in the mathematical sense, where normal means perpendicular. So if I have an object and I set it on a table here, it's going to be the same as what we've got going on here. There's a gravitational force pulling down on this textbook, same as on this olive oil. And then there's a normal force pushing upwards. And what will happen is the table will bend just a little bit. It's got a little bit of elasticity to it until the upward force balances the gravitational force, and then it will stop. So what will happen is these two forces will balance. Now it's always possible the table's not very sturdy and the object we set on it is really heavy and the table collapses. But in most of the examples we look at, we're imagining the table is sturdy enough to provide a force that can offset gravity. Let's see. In the horizontal direction, we have a frictional force. Clearly this time, this thing's sliding. It's what we call kinetic friction. That's going to create a frictional effect. And so we're pulling with a force. If this force is bigger than friction, then it's going to pick up speed. If this force is less than the friction, then it's going to slow down. If we pull such that the force here exactly balances the frictional force, then we will have constant velocity. Now the forces that we're looking at here, that vertically oriented one, the contact force, the perpendicular contact forces are called normal. I'm going to use a big N for those. So here I've used capital F all over. I'm going to start using big N. For friction, I'm going to use little f. And again, we'll look at friction in more detail next chapter. These are both contact forces. And what that says is I don't have a normal force, I don't have a frictional force, unless I have two objects in contact. In this case, we got the olive oil container in contact with the table. And then tension, when I have a string or a cable, I'm going to use big T to represent tension. And then it turns out that gravitational forces can be calculated. We can calculate what the gravitational force is by taking the mass of the object and multiplying by the gravitational field that we saw in the last chapters 2 and 3. So little g, the gravitational field, gets multiplied. That's a property of the Earth, we'll find out. Gets multiplied by the mass of some individual object, and that will tell us how large the gravitational force will be. Now the book likes to call this weight, but I think that creates more confusion. I'm going to call it the gravitational force, and I'm going to use the symbol mg to remind me how we determine the gravitational force. All right, so there's what's called Newton's laws of motion, and I guess if you're a contestant on Jeopardy someday, you're going to want to know what the first and the second and the third law are. The first law of motion, okay, there's a lot of writing here. It says if there's no forces at all acting on an object, if we can eliminate all forces, then the motion will be constant velocity. So, you know, this is kind of an interesting notion. This came up with planetary motion. People said, well, what is it that's, you know, the planets are moving in orbits. What is it that keeps them moving? And Galileo's answer was, they don't need anything to keep them moving. As long as there's no force acting on something, objects just keep moving. It actually requires a force to slow it down. And so forces are required to change the motion. That would be an acceleration. But if there are no forces, then the object just maintains constant motion. So this is Newton's first law. It's called the law of inertia. Objects at rest tend to stay at rest. Objects in motion tend to maintain that motion, and the motion will be uniform velocity in a straight line. So not only do you have to keep moving at the same speed, but it's the same direction. It's got to be one particular component in one direction that is sustained. Now, being at rest is actually a subcategory of constant velocity, right? So here we've got, oh look, there's the textbook right there. Okay, and they're sliding it along the table, and depending on which is the bigger force, is it the friction or is it the push coming from the hand, if F is bigger than friction, then it accelerates forward. If F is less than friction, then it slows down. If F matches the frictional force, it will maintain constant velocity. So this is introducing the idea of net force. Now in this conceptual example, it says, you know, you're riding along in a school bus, it comes to a stop, all the backpacks go forward. What is it that's drawing the backpacks forward? Well, here we go. Here is the school bus. Here's someone standing outside watching, and the school bus is moving at a constant velocity, and that means that the school bus is an inertial reference frame. Everything going on within the school bus can be analyzed in terms of any of the physics formulas that we've developed. So it's moving along at a constant velocity. Now, that includes the backpack. So what happens is, when the bus slows down, so now there's an acceleration in this direction, that requires a force. Now the bus slows down because there are forces between the tires and the pavement. That enables the bus to slow down. But the backpacks and the passengers won't slow down until there's a force acting on them. And so you need, the backpacks in particular, just keep moving forward. Now if you're on the bus, what that looks like is all the backpacks suddenly flew forward from within the bus. But when the bus is accelerating, it's no longer an inertial reference frame. So a person outside can call to the people inside and let them know, the backpacks just kept moving at constant velocity, and it was the bus that slowed down. The backpacks just kept moving. That's what gave the appearance as if something pulled the backpacks forward off the racks. All right, Newton's laws of motion hold in every reference frame. Not much to include from there. Let's move on and talk a little bit about mass. Mass feels like it should be a familiar property, but we want to be clear about what mass entails and how we are able to think about mass. Mass has two distinct properties, and I'm going to say it's a little bit of a mystery as to why mass works that way. But mass is a measure of how much inertia there is, and we saw that in that first formula, saying that the acceleration depends on how much force, but it also depends on how much mass. If there's more mass, it's going to be harder to accelerate an object. Now, mass is measured in kilograms, and it has property 1 is inertia, and that's a resistance to acceleration. Another way to state that is it makes it harder to change the velocity of an object. If an object's moving along, it's got a lot of mass, it's going to be hard to slow down. Mass is a property of the object. It stays with the object wherever it goes. If we were, if we're driving around in a car, you're driving around in your friend's car and it runs out of gasoline. And you go, oh great, we're going to have to push it. There's a gas station right there, let's push it down the street. You get out and you start pushing. Now you're pushing really hard and you're going, have you got that thing in neutral? Because it's hard at first to tell if you're getting much of an acceleration. Now if you're out there pushing and it's fairly level and the car's in neutral, little by little you'll see that it is picking up speed. And you go, there we go. We are getting an acceleration. We're pushing really hard. We're creating a lot of force, but the car has a lot of mass to it. Now, once it's headed down the street, you realize, oh, it's going to be hard to stop. We forgot to leave somebody inside so they could put on the brakes. You don't want to run around to the front of the car and try and slow it down that way. But so getting an object with a lot of mass, getting it moving, requires a lot of force. Slowing it down and stopping it requires a lot of force. So any change in the velocity is going to have that effect. Now there's a separate property of mass, property 2, and that's what's called the gravitational property. And that's not the same thing as inertia. So the second property of mass, the gravitational one, determines how large the gravitational force will be. So if we took your car to the moon, take your friend's car to the moon, again you're driving around, you run out of gasoline, is it going to be easier or harder to push it? And it's going to be the very same. So it's got just as much mass as it had before. Pushing on it, getting it up to speed, is going to require just as much force as it did back on Earth. Now, lifting the car would be easier because that would correspond to a gravitational effect. So the force of gravity pulling down on the car, on the moon, would be only 1/6, roughly, the force as the gravitational force pulling it down on Earth. But as far as changing its motion, that refers to the inertial property, and that will not have changed. So m stays the same everywhere the object goes. And again, the textbook is going to represent this as if we add all the forces together, we can set that equal to the mass times the acceleration. Sometimes I find students get confused with this. They start to think of the acceleration of the force, the acceleration as being a force. It's not. And so I always write it this way. I say that the acceleration is a result of the forces acting on the object, and to get the actual amount of acceleration, we have to take the forces and divide through by the mass. So anyway, that's going to be my approach for these problems. And so when we look at this in 2 dimensions, that says that any acceleration in the x will be a result of a net force in the x direction. Again, we got to divide that net force by the mass. Acceleration in the y will be a result of forces in the y direction. To find out how large that acceleration is, we add up all the forces in the y direction and divide them by the mass. Now the units of mass are, the standard units are kilograms. Chemistry, I guess, and biology maybe too, is more often working in the CGS system with grams. Now what's funny is in the British system, the mass unit is actually what's called a slug. We will not be using slugs at all. I'm guessing you've never heard of a slug. Now those are the mass units. If we look at force units, in standard international units, which we're going to use, the unit of force is a Newton. And the Newton is equal to a kilogram meter divided by seconds squared, and that comes from these formulas, or from this formula here. I've got to make the units match on both sides. If the force is in newtons, then the Newton unit is equivalent to a kilogram times the mass divided by seconds squared. So that's kind of interesting. Force units are just a combination of mass units with some length units with some time units all thrown together. Interesting. So in the CGS system, these are dynes. We're not going to be working in dynes. We're going to be working in newtons. From time to time, we'll talk about pounds. Now, you guys are probably familiar with pounds. So we've got kind of a mixed set of units here because we're used to thinking of pounds can be converted to kilograms. Strictly, that's not true because, again, kilogram is keeping track of the mass of the object. And so if I have a 10 kilogram object on Earth, it's going to be 10 kilograms on the moon. It's going to be 10 kilograms if it's out in deep space. It's going to have the same amount of inertia. It's going to require just the same forces to accelerate an object with that 10 kilograms regardless of where it is. Now, pound actually refers to force. And so pounds, when we measure something in pounds, it's usually asking how much gravitational force is acting on it. And so a 10-pound object on the Earth would not be 10 pounds on the moon. It would be 1.7 pounds, roughly. So the slugs would stay the same. So if it was a 5-slug object on Earth, it would be 5 slugs. And the way this works, yeah, I think we're just going to move on from that. Okay, enough looking at those units. So it says that here's what we're going to be doing for the next several weeks, maybe for many, many weeks, in the next many, many chapters. We're going to be isolating objects, identifying forces. This is kind of the force diagram that we've seen. Here is the gravitational force. Here is the normal force. That's a contact with the surface. Here is the frictional force, also a contact with the surface. And here is some kind of a force. Maybe it's a tension or something. We're pulling on it in this direction. The force diagram will have the object drawn, all the forces drawn and labeled, and then off to the side, arrows for velocities and accelerations. So the forces get to be right on the object, only the forces. Accelerations and velocities, they're not forces, they're kinematics. That was chapter 2 and 3. So get those off the force diagram, away from it. Make sure they're there, they're useful, but put those off to the side. That's what a force diagram looks like. These are also called free body diagrams. In other words, isolated object diagrams. So that's a free body diagram, and there's two possibilities. I'm going to say, let's create some categories here of what's going on. Either the F net is 0, or the F net's not 0. Now, F net being 0 in the y direction would say n equals mg. F net equals 0 in the x direction would say big F equals little f. If there's no net force, then the motion will be constant velocity. That means that the acceleration is 0. Now, being at rest it falls into the category of constant velocity. So if there's no net force, the object could be at rest. It could also be moving. Either of those are constant velocity. Either of those would have no acceleration. Now, what if there is a net force? What if, yes, net force, then the velocity would be changing. As a result, the acceleration cannot be 0. And so, depending on x and y directions, see how we've listed this. Here is the formula. We add up all the forces using vectors, what we've learned with vectors, divide through by the mass, and determine the acceleration. What that's really telling us is we add up all the forces in the x, divide by the mass, to determine the acceleration in the x. Same thing in the y. Add up all the forces in the y, divide through by the mass of the object, and that gives us the acceleration in the y. So there's going to be plenty of examples. Let's say in this example that in the y direction, n equals mg, those two forces cancel. There is constant velocity in the y direction. But big F is bigger than little f, and that means we will have an acceleration in the x. So we look at this component by component to see which direction the accelerations are going to be in. This is, it's a good set of diagrams and items here to stare at and think about. That's how we're going to be setting up every last one of the problems that we're going to be looking at. So let me go back and say one more thing here. Sometimes we say, well, what if all the forces are removed? What would happen? Well, if all the forces were removed, clearly that would lead to no net force, and that would lead to constant velocity. So whatever velocity the object has, it would just maintain that velocity if there are no forces. Now, the problem with that is, how do we actually eliminate all the forces? So if I'm looking at a diagram here, let's say that the surface is frictionless, so there's no friction force, that's gone. Let's say that we're not pulling on it at all. So if we're not pulling on the object, then there's no friction. That says that in the x direction, there's no net force. This object should keep sliding along the surface at constant velocity if there's no friction, if we're not pulling on it. Now, in the vertical direction, we could get rid of n, but getting rid of the normal force would mean lifting the object off the surface. And if I lift the object off the surface, well, now I'm holding on to it. What if I let go? Well, if I let go, the gravitational force is still acting on it. That gravitational force is hard to get away from. So we really don't have many situations. I'm going to say we're not going to really be looking at any situations where all the forces are gone, because almost always, maybe always, we're going to have some kind of gravitational force acting on the object. The way to eliminate gravity would be to take an object far, far away from all the other objects in the universe to minimize gravity, but gravitational forces are almost always going to be there. All right, now let's go back and very quickly, let's think of an object with mass. Now, another thing I want to point out is it's very unfortunate that in our language we have started to use the word massive very frequently. People go, oh, that was just massive. Oh, that thing is so massive, where it doesn't really mean it has a lot of mass. We frequently use the word massive to mean that it has a lot of volume. You know, oh, look at that bridge, it's massive. Now, you know, the bridge probably does have a lot of mass, but usually when people say that, they're thinking in terms of how much volume it has. So, again, one of those unfortunate things that comes up. So, you know, when you hear people using the word massive, remember that's not really appropriate for what we're calling mass here. Very, very likely. Anyway, I've got an object, it's got a certain amount of mass. I'm going to apply just one force. I'm going to imagine somehow I'm doing that. That's going to create an acceleration. Now, the mass of this object, if it's 1 kilogram, and if the acceleration we want is to have 1 meter per second squared, then the force we need to push with would come from taking m times a, and that would give us 1 kilogram times 1 meter per second squared. That is how 1 newton of force is defined. Now, for kind of a reference here, 1 pound of force is about 4.5 newtons. So 4 or 5 newtons equals a pound, just for comparison. Okay, very same object, very same force, very same acceleration, but this time I'm going to use British units. Now, for this, I'm going to have a mass of 1 slug. Okay, and I know I have a hard time working with slugs also. So, and I know you guys are probably brand new to this. So let's think of a mass of 1 slug. Actually, the acceleration's not the same and the masses aren't the same. Sorry. This mass is going to be 1 slug. The acceleration we want is 1 foot per second squared. So what we're doing is we're setting the masses in the units in that particular system, and we're setting the accelerations also to be 1 foot, that would be the standard unit, in British units, divided by seconds squared. So they both use seconds. So this acceleration, now the force that would be needed to take something with 1 slug of mass and accelerate it at 1 foot per second squared works out to be a pound. Now, in terms of conversions, 1 slug is equal to 14.6 kilograms. That's how it works out. That's a lot of mass. 14 kilograms. I mean, each kilogram is like a liter of water. So a slug would be the mass of, 15 liters of water would be just 1 slug. Now the accelerations here, 1 foot per second squared, feet are shorter than meters, and so 1 foot per second squared is only 0.305 meters per second squared. So if I take the slug, multiply it by the 1 foot per second squared, that gives me a pound. And over on this side, I can take the 14.6 kilograms, multiply by 0.305 meters per second squared, and find out that the conversion between pounds and newtons is 1 pound is 4.45 newtons. So that's how the conversions work out between slugs and kilograms, feet per second squared, meters per second squared, pound, and newtons. So if you watched the moon landings, if you've watched, it was the 50th anniversary of the first Apollo moon landing a couple of years, a while back, and a few years back. And if you listen to the engineers at NASA and the astronauts talking to each other, it's all in feet per second, right? All the velocities are in feet per second, the accelerations are feet per second squared, and the forces are in pounds. And so those were the units that everybody was trained in and worked at that time, and it works. Another set of units does work. The International System of Units, of course, has the advantage that everybody is kind of on the same page. And we introduced the possibility of catastrophe if we're not paying attention to units when we're communicating. I'm sure you guys, maybe you guys have heard of stories where the units were misunderstood, and as a result, you know, I guess it was a Mars landing, right? Where one of the spacecraft crashed into Mars, and it was traced back to a misunderstanding about what units were being used to represent the forces and the velocities. Let's see. So let's try this out. Here is an automobile. It's starting at 100 kilometers per hour at x equals 0, and it's going to slow down and stop. Now when it stops, it's going to be at 0 velocity, and during that time it will have traveled 55 meters. And notice they're using the front of the car to keep track of distances. So what they're saying we are supposed to do in the problem is, let's say that oh, there's two examples here. This is actually for example 3. In this one, we're speeding the car up. So in example 2, we got a 1,000-kilogram car, and we want to accelerate it. I don't know why they write the 1/2 g. I actually would prefer they not do that. It is a useful reference. We'll talk more about that when we start looking at the problem. They said how much force would be needed to accelerate a car, how much force would be needed to accelerate a 200-gram apple. All right, so let's take a look at that and see. Here is that first problem. Here is a car. It's got a mass of 1,000 kilograms. Does that make it massive? I'm not sure. Anyway, it's got a mass of 1,000 kilograms. That's an inertia property. Here is an apple. It's got a mass of 200 grams. And what we're going to do is we're going to come up with an acceleration which is 4.9 meters per second squared. Now, where the 4.9 is coming from, if you remember, they said that the acceleration was going to be at 1/2 the value of the gravitational acceleration, and Earth's gravitational acceleration is 9.8, so I divided that by 2, and I ended up with 4.9 meters per second. So in order to accelerate that car at 4.9 meters per second squared, I'm going to need 4,900 newtons. But to accelerate this apple at the very same acceleration, it has much less mass, much less inertia. It's only going to require 1 newton, a little less than 1 newton. So 4,900 newtons versus 1 newton, and that's because the car has 4,900 times as much mass as that apple does. Now there was a problem 3 that they slipped in there, right there. And they're asking about how much force would be required to slow this car down. So this is a really good example. This is kind of our first example, I think, where we're taking forces and using those forces to determine or calculating forces related to a certain acceleration. So what they're saying is that the car, I wanted to get the initial velocity. Oh, this car is 1,500? Did they really change the mass? Or did I misread it? This is a heavier car. It's got more mass. So this is a 1,500 kilogram vehicle, and it starts out traveling at 100 kilometers per hour. Now, kilometers per hour are not standard, so I'm going to write that as 100,000 meters per 3,600 seconds. I need to do a units conversion. It turns out the velocity here, in standard units, is 27.8 meters per second. That's what it really is. So let's work from that. So this is going to be 27.8 meters per second, and as a velocity. And now what I'm going to do is go back and bring into chapter 4 some of those equations that we had derived for constant acceleration. We're going to assume that the car is undergoing a constant slowdown over the 55 meters. So it starts out at 27.8 meters per second. There's a constant slowdown, and after it's traveled 55 meters, it will have stopped. So I'm putting all the numbers in here, and I'm solving the equation for A. Actually, I'm doing it, solving the equation first. So I'm going to do the algebra first. V squared minus V naught squared over 2x. And Here is the v, here is the v naught, here is the x, and it tells me I need an acceleration of 7.01 meters per second squared, and the minus sign is telling me that acceleration will be in the direction opposite to the velocity. We said the velocity was a positive number, and when we did that, we defined this direction to be positive. So acceleration is in the opposite direction. It shows up with a negative sign. Okay, so everything up to here is chapter 3. Now we're going to say how much force is required, and to do that we can take the mass, multiply by that acceleration, and that says we're going to need 10,520 newtons. Now it's got a negative sign on it, but you wouldn't, if you were talking with a colleague, you know, if you're analyzing the braking system of a car, you probably wouldn't call the force negative. You would just say we need the brakes to be able to provide a force of 10,520 newtons in order to stop the car in 55 meters. So I've dropped the minus sign and allowed the diagrams to tell the story in terms of directions. So the velocity is, if the velocity is this way, then the acceleration is going to need to be opposite, and the force needs to always be in the direction of the acceleration. So it's force and acceleration that are always in the same direction. Interesting. And we're going to need those 10,520 newtons to provide for this. Okay, so we kind of hurried through Newton's second law of motion, and so the first law was saying that objects tend to maintain motion in the absence of force. They'll maintain constant velocity. The second law was actually the formula we've been using. So let's go back and see if that, there we go. That is the second law. I mean, that's another variation of it, but that's considered the second law. Now, the first and second law are both in that formula. The first law says if there's no forces, then there's no acceleration. The second law says the acceleration is determined by adding together all the forces and dividing by the mass. So first and second law. Now the third law says that when we have contact forces, when we have something coming into contact with something else, here I am contacting the wall, the force acting on my hand due to the wall, and the force acting on the wall due to my hand, those are going to be the same magnitude. It's going to be the same amount of force. So the force exerted by the hand on the desk, that's backwards, isn't it? Yes, it is. Oh no, 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 it's right. The force exerted on the hand is this force here. So when the contact is made, immediately what happens is we have forces acting on each of the two objects. Now remember, there are two distinct objects. It's not two forces acting on the same object. It's two forces acting on different objects. So the hand will experience a force, and the table will experience a force. Now those two forces will be directed exactly opposite each other, and they will have the same magnitude. So we can refer to this as a force pair or an interaction between two objects. It's not the same object, two different objects. And these work in the example of contact forces. Now, that's the third law. Now, what about gravity? Did Newton intend the third law to apply to gravity? And he did. So the idea was that the Earth and the Moon exert gravitational forces on each other, and the Moon is pulling on the Earth, and the Earth is pulling on the Moon, and those amounts are equal. Newton's understanding was that these forces occurred instantaneously. So right at the same instant, the Moon and the Earth are experiencing the same force. We now understand that gravity has a delayed effect. It doesn't cause any difficulty for any of the examples that we're going to be looking at. But just for your information, just for your understanding of how this works, gravitational forces take a little bit of time. So, for example, the gravity that planet Earth is experiencing right now, due to the presence of the sun, the sun's gravity is holding us in orbit. We're actually experiencing the gravitational field that the sun generated about 8 minutes ago. Gravitational effects propagate at the speed of light. And that has to do with how space and time are put together. So it doesn't really have to do with light. It has to do with the space-time continuum, and general relativity explains to us how that works. So it's kind of interesting to think, well, the third law doesn't quite work, does it? Because for contact forces, this works fine, because when the two objects come into contact, that's simultaneous, they both feel the forces, they're right in direct contact. Newton himself worried about this idea that objects at a distance could exert forces on each other, and that the forces could be simultaneous. That was kind of a mysterious idea, but the formulas worked. So the formulas that Newton developed, they work really well. We're going to see them in chapter 6. Just realize that there's a little tiny bit of a limitation there, because gravity is not instantaneous. It turns out that electric and magnetic forces also propagate at the speed of light. Again, it's due to the properties of the space-time continuum, and so they're not quite instantaneous, but for our purposes, we can treat them as if they are. Okay, just a brief discussion about forces and the third law. Here's another example. Here's a person pushing on the wall. There's no way that this person can exert a force on the wall without the wall exerting a force back on her. And so maybe she's pushing away from the wall, so she's at the wall, or maybe she's run into it, I'm not sure which. So maybe she's coming from the side and using the wall to slow herself down, and during that time she pushes on the wall, and that slows her down, or it pushes her away from the wall. But these two forces will be the same magnitude, and they'll be directed oppositely, and they'll be acting on two different objects. Now, this third law, Newton's third law, solved so many problems for me as a parent with my kids when they were growing up, because, one of the kids would come up and say, "Hey, he hit me." And I would say, "Well, what do you mean he hit you? And the forces must have been in both directions. You both hit each other." And they go, well, he hit me harder. And I go, well, that's just not possible. These are contact forces we're talking about. And, if he hit you with 40 newtons, then you must have hit him back at 40 newtons. And then he'd say, well, but he hit me first. And I go, no, it's simultaneous. So if you're pushing, if he hit you with 40 newtons right at the time when that contact was made, you were also pushing back at 40 newtons. So yeah, third law works really good for parenting. All right, let's see. Here's another example. They like these. They're saying, okay then, how does the third law operate here? How do we get the space shuttle to launch? Another great view of that. What are the forces at work here? So rocket propulsion, they're claiming, can be thought of in terms of Newton's third law. Now, these are contact forces. I disagree with, I guess I think this is not, I disagree with the way this is stated. It says, notice that the rocket does not need anything to push against. And if it's a force pair, then there's going to be a force pushing the rocket upwards. That's what we call thrust. There's got to be a force pair going along with this. What is it? And so what's pushing the rocket in this direction are gas molecules generated from this violent chemical reaction. So when these gas molecules are moving very quickly, when they go to high temperature, they're generating this chemical reaction, they're at high temperature, they push very forcefully into the combustion chamber of the rocket. Now that's part of the rocket, so these gas molecules push against, and when they make contact, the gas molecules and the combustion chamber of the rocket engine push away from each other. So the rocket is pushing down on the gas molecules, and those gas molecules get redirected downwards, and the gas molecules are pushing upwards on the rocket, the metal combustion chamber inside the rocket engines, and that propels the rocket upwards. So there definitely are two different objects pushing against each other, and the gas molecules get pushed and directed downwards, and that leads to forces pushing the rocket itself upwards. Okay, we are getting close to break here. I would like to get maybe one more example, and let's see. Let's say, here's a conceptual example. What forces do we need to move a car? A common response is that the engine makes the car move. How is friction involved? Let's jump ahead. I think I've got some diagrams we can talk about. Okay, so this is, I think it's a very important example. Here's a car. What we want to do is we want the car to accelerate. So I'm going to claim this is an all-wheel drive vehicle, and we would like the object to accelerate. Maybe it's already moving in this direction. What are all the forces acting on it? Now I'm going to start with gravity, and gravity is acting on all parts of the car. All parts of the car are experiencing a gravitational force. Now if I combine the car into kind of one object, I can take that gravitational force, mg, and I can treat it as being applied at that one location at what we call the center of mass, or the center of gravity for the car. Now the normal forces, we've been drawing the normal contact forces vertically, perpendicular to this horizontal surface, and those normal forces are actually coming about as a result of contact with the pavement. So there's not just one normal force going on here. There's four normal forces. There's a normal force at each one of the car's tires where it comes into contact with the pavement. So that's where the normal forces are going to be. Now, how am I going to get this car to pick up speed? And what I'm going to do is I'm going to have an engine. The car's engine is spinning around. It's connected to a drive shaft or a set of gears or something. So there's going to be a drivetrain that leads to the four wheels, and it's going to cause the wheels to go this way. Now, when the wheels go this way, when the tires go this way, there's a couple possibilities as to what happens at the contact point with the pavement. So when the tires begin to go, if there's not good traction, the tires can just spin, and the car is sitting there with the tires spinning, right? Now that's not making the car go forward. What we do want is to have friction between the pavement and the tires so that when the tire begins to spin, the traction holds the tire against the pavement, and as a result, the tire moves forward. Now that's a frictional force, and it's actually a good example of a third law, frictional force pair. So there's a frictional force from the pavement pushing the tire forward, and at the same time the pavement is experiencing a force backwards. Again, two separate objects. The car is being pushed forward, the pavement is being pushed backwards. If you moved into a frame where we're walking along right with the car, what we would see in our reference frame is the car's wheels are going around and that the pavement is going in this direction. So again, if we move into the reference frame of the car, maybe we're in another car filming it or something, what we would see is the pavement is moving by and these wheels are going around. The pavement has a force pushing it in that direction. The car has a force, frictional force, pushing it forward. So that's important. So we use frictional forces to control the motion of the car. We're using the traction between the tires and the pavement to make sure the car doesn't slip. We want that to be what are called static frictional forces. And we control speeding up, slowing down, turning left, turning right, it's all done with frictional forces, as is walking. So walking is also done using frictional forces. If I'm standing here and I want to accelerate, I want to pick up some speed and walk somewhere else, excuse me, I am going to depend on frictional forces, setting up frictional forces between my foot and the floor, or my foot and whatever I'm standing on. I've got to be able to set up frictional forces. If we have no friction at all, we realize that if this is a frictionless surface and we engage the engine, we put it in gear, the wheels are just going to be rotating, but there won't be any frictional forces to push the car forward. Same thing if I'm walking. If I'm walking and it's a perfectly smooth, icy surface, I can't control my motion. I'll just go into constant velocity and slide across the ice. So frictional forces are important for operating our cars and for walking. Okay. All right, that's a good place to take a break. Let's take a break for, I guess the standard here is 10 minutes, and then we'll come back and talk some more chapter 4, forces and acceleration.